much in line with what we do as a committee. We also have a number of activities that we do at the annual meeting. We coordinate and host a master class during the student sessions. That's where we divide students into small groups, assign a mentor forecaster to each group, and go through an interactive forecast scenario. The past 3 workshops we've focused on severe weather, heavy rain, and winter weather. We also coordinate the daily weather briefings. We have a forecast mentor, a student or group of students, and those students in turn provide the daily weather briefing at the annual meeting. And finally, at the annual meeting, one of our activities is to coordinate and manage the student poster and presentation competition. And so that is something where it involves a lot of people. We need lots of judges for that. We always need more help than we have committee members with all of our activities at the annual meeting. So if you are going to be at the upcoming annual meeting and you have an interest in helping out, please let me know. You can find my contact information on the WAF committee page of the NWA website. With that being said, we've got a great talk lined up for you on QLCS tornado warning, specifically revolving around a day in South Central Texas. Our 2 speakers will be Jared Allen and Brett Williams. Jared Allen currently serves on the Weather Analysis and Forecasting Committee. He received his undergraduate degree in operational meteorology and master's degree in GIS from Mississippi State University. He was a SCEP intern and general forecaster at the National Weather Service in Jackson, Mississippi. And he's now a lead forecaster at the National Weather Service in Austin, San Antonio, Texas. His primary research and projects include GIS river flood extent mapping, utilizing the NSSL flash data for flood awareness, and enhancing WFO severe weather messaging and service. Brett Williams will be the second speaker. He received his bachelor's in atmospheric science from the University of Missouri and his master's in atmospheric science from the University of Alabama in Huntsville. He spent about a year as a research associate at the Warning Decision Training Division before joining the National Weather Service in Austin, San Antonio in May of last year. His primary research interests are the connections between total lightning and severe weather and QLCSs. So who better to give this talk? And with that, I will let Tricia hand it over to Jared and Brett.
Already done. Let's unmute them and take it away, Jared.
Thank you, Tricia, and thank you, Dan, for that wonderful introduction. Hello, everybody. This is Jared Allen alongside my colleague, Brett Williams, and today we will be talking about a very unique case, as we'll discuss, on the QLCS tornado event that occurred on the 19th and 20th of February, roughly a month and a half ago here in South Central Texas, that really impacted a good portion of our area, especially San Antonio Metro, moving up northeast into the I-35 corridor towards Austin, that actually produced a grand total of 9 tornadoes over the course of about 2.5 hours. So going back into the tornado database, we compiled the information and saw that only 24 noted tornadoes had actually happened ever in the month of February. And all the way back through 1950, it's only 24. In this particular case, we had 9. So that's just over 1/3% of all of the tornadoes that we have ever had in our particular area, South Central Texas county warning area, that is accounted for from this particular event. So it was certainly a pretty rare event, and that's why we really wanted to do a case study on it, and utilizing the 3-ingredient Tornadic QLCS method to enhance awareness and of mesovortex generation, intensification, and tornadogenesis, where a lot of research has been done up in the Central Plains, mid-Mississippi Valley, and across portions of the East Coast. But we really wanted to apply this method and see exactly how it worked out, which indeed very well, for this particular case. So moving forward, we're just going to do a brief outline on the background of the 3-ingredient QLCS vortex method based off previous research. We're going to break each ingredient down, looking at the balanced and shear dominant regimes of a QLCS structure. line normal shear within the 0 to 3 kilometer bulk shear values, usually greater than 30 knots based off previous research. And obviously always looking for bowing segments or surges in the QLCS line. From there, I'm going to transfer it over to Brett, where he is going to do the Tornadic QLCS radar mesoscale analysis, putting all the research pieces together and then applying it to the actual radar signatures that occurred. And then at the end, we're going to wrap it all up really nicely, looking at the best practices for utilizing the 3-ingredient method from a warning coordinator perspective, potentially even from a radar warning operator perspective as well. So here's kind of a teaser slide before we get into the research. There on the left, at 430Z, you have the reflectivity, and then on the right, 430Z, the complementary storm relative motion or velocity. So overlaid, we have the 0 to 3 kilometer shear vector on both sides. And as you can pretty much tell, you got a well-balanced, well-defined kind of surging line right here, over here on the reflectivity. And then complementary to that, over here on the right, you can certainly start to see the well-balanced updraft, downdraft correlation of where those inbounds and outbounds really clearly define the updraft, downdraft convergence zone. So understanding QLCS tornado environments and warning challenges is a continuing issue within the Weather Service, and it's always very difficult sometimes to ascertain when a QLCS is outflow dominant, when it's going to become more better balanced, when you potentially have a surge or outflow, and then depending on your mesoscale environment of your wind shear, at what point is it really going to want to start generating mesovortices? Are those mesovortices going to potentially intensify? And if they do intensify, will they be able to produce tornadoes? So that's really what we're going to be talking about a lot today. So here you can kind of see in that white dashed line where that updraft, downdraft interface is, where you diagnose the radar and velocity signatures that can lead to the intensification of mesovortices. You look at the lining up of those 3 ingredients, as you can see over there on the right, which we'll get into a little bit. And then especially you determine where an enhanced tornadogenesis threat location will be moving forward in time. So as a radar warning operator or as a warning, event coordinator, you could be calling out these different features to your staff or to your warning operators just to make sure that everyone is as situationally aware as possible during these fast evolving situations. And in this particular case, this is exactly where we had 4 tornadoes get spawned from, where we had 4 tornadoes develop over the course of the next half hour to hour within that zone. Most notably that EF2 that happened in the northern San Antonio metro area. So Schaumann and Pryzbylinski of 2012 did a severe local storms paper where they looked at the operational application of the 0 to 3 kilometer bulk shear vectors in assessing QLCS mesovortex and tornado potential, where they analyzed a lot of QLCS cases from the plains all the way over to the East Coast. So in this image right here from the COMET program, a lot of QLCSs and NCSs produce a cold pool, as you can kind of see here in this light blue. Well, depending on how much shear is present within the environment, that cold pool will really enhance or de-enhance the updraft, downdraft convergence zone, depending on how much shear is present. So you get a lot of you get a lot of horizontal vorticity rotors, so to speak, that occur along that updraft, downdraft convergence zone, where you have that cold pool going across where you have that shear balance. So throughout this presentation, you'll hear quite a few times the updraft, downdraft convergence zone. So just to kind of put it all together right here, also from the COMET program, if you have a dominant cold pool, very strong cold pool from a QLCS or from MCS, and very little to no shear there on the bottom left, your updraft, downdraft convergence zone is not very strong, nor does it really extend very high into the atmosphere. But if you look at the balanced cold pool and the shear values there in the middle, you can see that your interaction of the updraft, downdraft convergence zone is much greater and more enhanced, where you get much greater tilting of that horizontal vorticity that occurs with those rotors. So if you have that horizontal vorticity, and you have that stronger updraft, downdraft convergence zone, it's able to tilt that horizontal vorticity obviously into the vertical for greater mesovortex generation and then potential intensification that could eventually lead to tornadogenesis. And then even over there on the far bottom right side in the dominant shear regime, you do still have an enhancement of the updraft, downdraft convergence zone that's able to really take care of some of that horizontal vorticity and changing it more into the vertical. So one of the first ingredients here, highlighted here in red, is you always want to look for balanced to slightly shear dominant areas on radar, looking at radar signatures, because those locations are more efficient at the vertical tilting and stretching of that horizontal vorticity. And as we move forward, if anyone out there is taking notes, anything that kind of has that little key emblem is kind of the big takeaways for that particular slide and this particular presentation. So real quick, how do we locate that updraft, downdraft convergence zone, and especially that balanced to slightly shear dominant region? So from that previous research, from this case up in southern Missouri back in 2015, you locate the updraft, downdraft convergence zone using the velocity and SRM products compared to your reflectivity products. So in this particular case, you have a radar that's a little bit further up to the north and west. You have your outbounds there over Ava and Squires. You have a pretty good mid-altitude radar convergence signature with your inbounds there on the other side of Douglas, just to the east. And then complementary to that, you can tell exactly where that updraft, downdraft convergence zone is relative on reflectivity, where it kind of tucks back into the reflectivity, where you have that slightly shear dominant region, you have that little inflection point, and where you have that balance location there near Douglas. A little bit farther south and to the west, you are slightly cold pool dominant there. So in applying that first ingredient, the first area that a radar operator, or if you're arm chasing at home using GR analyst, then the first spot obviously is going to be looking in this area just to the northwest or right near Douglas for potential mesovortex generation. So we will hold on to that first ingredient there, number one, and then we'll move into the second ingredient here. So the previous research also looked at the analyzation of the 0 to 3 kilometer line normal shear magnitudes relative to the QLCS motion. Excuse me. So what they approximated and what they found over a lot of their cases was that a 3 kilometer shear depth, the 3 kilometer depth appears to be a good approximation for the typical cold pool depth near that interaction of the updraft, downdraft convergence zone. So we really want to isolate the shear that is acting on those particular rotors, the horizontal vorticity that's able to be stretched vertically to create the mesovortices and potential tornadogenesis if everything aligns correctly. So what they ended up finding is that anything greater than 30 knots or in and around 30 knots of 0 to 3 kilometer line normal shear really helped produce greater intensification of mesovortices and thus tornadogenesis. But some may not be quite familiar with what line normal shear is. So we have this kind of very rudimentary squall line right here moving directly west to east. And if we have a 0 kilometer shear vector of 35 knots kind of oriented at about 30 degrees above east, so that's roughly about 230 degrees from the southwest, we have that particular shear vector. So what is the angle difference between those two? So if we approximate that squall line with that updraft, downdraft convergence zone due north-south, and then we apply that 35 knot vector off of that particular line, we really want to know that value of X right there, which is the line normal shears. So using pretty simple trigonometry, we're able to use the cosine of that particular angle, which is the adjacent X over the hypotenuse, 35, and then we're able to deduce that real quick through math, or you can use your iPhone calculator or even go on to Google and do that really quickly. And this equates to roughly about 30 knots of your line normal shear. So like I was saying earlier, what they found over many cases studied is that their 3-kilometer line normal shear magnitudes around or greater than 30 knots correlate to increasing likelihood of mesovortex generation and tornadoes. So there's our 2 ingredients. What's that third ingredient? Also, what about the difference between QLCS directions and the shear vector orientation? So here are 3 separate different cases. So instead of 35 knots, now we're looking at 40 knots. We have that same squall line moving directly west to east. And you do that arithmetic real quick, you get 35 knots. Looks good, satisfies the ingredient. How about if that same squall line is moving directly northeast? Well, then your angle goes very low, if not near 0. Cosine of 0 is 1, and you're really cooking right there. So if you have any surges or bows, or if you have a particular squall line well oriented with your 0 to 3 kilometer shear vector like that, it's going to be very likely to want to produce mesovortice generations. How about if it's moving to the southeast? Well, we're kind of running into a little bit of a problem there. If you have such a great angle, say at 50, 60, 70 degrees against what your 0 to 3 kilometer shear vector is, then you're not quite satisfying the ingredient at that particular point. So as a warning operator or as an event coordinator, obviously you have to be very cognizant of the angles of your 0 to 3 kilometer shear vector, as well as the forward propagation motion of your MCS or your squall line. So obviously we don't sometimes have a prototypical totally vertical north-south oriented squall line like this, right? So what happens when parts of the line surge and bow out? We have something that looks more like this sometimes, where you'll have different parts kind of moving different directions. So you have different line normal shear vectors kind of acting differently on different parts of that particular QLCS squall line. So in this particular case, that little middle section might be moving relatively 50 degrees of your 40 knot kilometer shear vector, and you don't quite satisfy that particular location for the ingredient. So that location may not be quite as favorable for mesovortex generation and thus maybe future tornadogenesis. What about that northern aspect? Uh-oh, now we're looking at a much lower angle relative to your 0 to 3 kilometer shear vector, and now you're satisfying the criteria there. How about that other section down there? Looks like it's satisfying that as well. And even that far south section, maybe not so much. So as we move forward, we can certainly see how the different directions and different bowing segments or surges along lines can really be important in relating to mesovortex generation. So for this third ingredient, kind of wrapping it all up from this previous research, we're really looking for surges or bows in the line due to either rear inflow jets or local outflow enhancements that occur.
Hey, Jared.
So, yes.
This is Tricia. I'm sorry to interrupt. We just took a power hit at the office. I want to just check with Dan to make sure that he can see what we're doing still. Dan, do you still have the view?
Yes, I do, and the slides are advancing just fine.
All right, great. I'll back out again. Thank you.
No problem. Wouldn't be a severe weather talk without severe weather. So in summary from Schaumann and Pryzbylinski of 2012, their summary really comes to fruition through the potential of mesovortex generation and intensification greatly increases when you have all 3 of these ingredients or properties coexisting within a QLCS or some type of MCS structure. So one additional study that was done shortly thereafter by a Holland scholar in 2013 looked at those 3 ingredients and then tested them over 90 QLCS cases across the domain that you see right there. And then based off all of those QLCS cases, they were able to denote about 67 mesovortices. And then out of all of those mesovortices, they were the 2 ingredients that were always present was the line that was either balanced or slightly shear dominant, and you always had a local surge or bow in the line. In addition, all mesovortices were associated with a surge or a bowing segment. So that's what we really need to look for, obviously, as a radar operator and as a event coordinator to manage and make sure situation awareness is high, they were always looking for the surges or bows, and then where everything is balanced or slightly shear dominant. And in their study, they were able to correctly predict almost 80% of all mesovortices with all three ingredients present. So some quick box and whisker plots. They separated the mesovortex producing surges versus non-mesovortex producing surges. So you had the surges all the time, but what surges produce mesovortices versus non-mesovortices? Well, whenever you had surges that had greater line normal shear values greater than 30 knots, that favored the mesovortex generation versus the ones on the right side that did not produce the mesovortex because of the line normal shear being generally less than 30 knots, where you can see that mean somewhere around 25, 26 knots versus the 33 to 34. Also, surges can also happen all the time. They can happen whenever the line normal shear is less than 30 knots or greater than 30 knots. But again, the mesovortices occurred generally whenever that line normal shear was greater than 30 knots. So, excuse me. So this further indicates and builds upon the previous research of Schaumann and Pryzbylinski from 2012. And then one of the bigger takeaways is looking at the bulk and line normal shear for all tornado reports. So when you have the bulk shear and the line normal shear, generally your line normal is going to be a little bit less because of your angle differences, but you can clearly see that the mean and the interquartile differences on these box and whisker plots show that whether it's bulk shear or line normal shear, your tornado reports generally are much greater than 30 knots, where you have because of the higher magnitude of that horizontal vorticity getting stretched for tornadogenesis. So putting all the pieces together, all the research pieces, we have a balanced to slightly shear dominant area in the QLCS. You have greater than 30 knots, 0 to 3 kilometer line normal shear. And then you are always looking for surges or bows in the line due to either rear inflow jets or locally enhanced outflow along that convective gust front. And then, of course, all mesovortices, at least based off previous research, have been associated with that surge or a bowing structure. And then that line balance, especially balanced to slightly shear dominant ingredients, are present in all mesovortices. So kind of having these 5 ingredients or these 5 ideas in the back of your mind as you're a warning coordinator or a actual warning issuer is really critical to understand potentially how the future behavior of the QLCS may transition to, from if it's a weak outflow dominated section and then it starts to surge and bow, and then that aligns well with your 0 to 3 kilometer line normal shear vector, and then it becomes balanced. Well, all of a sudden you're really cooking with gas there. So at this particular point, I'm going to hand it over to Brett to kind of apply these 3 to 5 points into the actual event that occurred here.
All right, thank you, Jared. Jared did an excellent job going through the background research on the 3-ingredient method and kind of setting this all up for us. Before I dive into the event here, Jared already touched on this, but these are our severe weather reports across our kind of warning area from 1955 to 2013. And tell you where there is highlighted, and you can see that we've only received 24 tornadoes across our CWA since 1955. So again, just highlighting the fact that this is a fairly rare event for us. This is a little thing we put together after the event, showing all of our tornado paths and some pertinent information. So just kind of reviewing the event, we had 9 total tornadoes confirmed, and these occurred between about 10:30 p.m. on the evening of the 19th to about 12:30 in the morning on the morning of the 20th. So it was a nocturnal event. These 9 total confirmed tornadoes, 3 were EF2, 2 were EF1, and 4 were EF0. We also had numerous significant wind damage events as well. It was the most impactful QLCS event that we have had in our CWA in over a decade, and this particular event tied for the largest February tornado event in recorded history, or since 1955, for our CWA. So the focus of this isn't exactly a synoptic overview, but it's always helpful to have some context from the synoptic setup. So this is the 500 millibar analysis from 0Z on the 20th or 6 p.m. local time here in South Central Texas. And the first thing you can see is that we have a high amplitude trough across southwestern United States and in northern Mexico. The trough is moving northeastward, so yielding height falls and positive vorticity convection for widespread forcing for ascent across our area. We also had strong south-southwesterly flow from northern Mexico through central Oklahoma up to about 60 knots, creating fairly substantial deep layer shear across our region. And this is a NAM model forecast sounding at 6 p.m. at San Antonio International Airport. And at this point, you can see we have fairly low LCLs, less than 750 meters above ground level. We have ample boundary layer moisture, and our surface dew points were in the mid-60s. We had sufficient stability, or greater than 1,500 joules per kilogram of surface-based CAPE. At the surface, our winds were about 10 knots out of the southeast, convecting ample moisture from the Gulf of Mexico. And 500 millibars, we were at about 65 knots out of the southwest. So just kind of a little background there for the synoptic setup in the environment. This is the Storm Prediction Center Day 1 convective outlook that was issued at 1Z on the 20th or 7 p.m. local time. And you can see that we were under a slight risk for severe weather, 15% hail, 15% wind, no hatch on either of those. Tornado threat was thought to be minimal, 2% probability, and that's both from the SPC and our office here. Tornado threat was thought to be fairly minimal. Definitely a significant tornado event was not anticipated. So the event began around 006 p.m. local time. Initially began with semi-discrete cells across northern Mexico and our western counties into the Edwards Plateau and the western hill country. Had some sporadic wind damage and marginally severe hail, but that's about it. As we go forward here to 2Z, or 8 p.m. local time, you can see the cells have grown upscale and congeal into a QLCS. Not particularly well organized at this point, but we did have some strong or 60-plus knot winds beginning developing east of the leading edge of the QLCS within that encircled region there. So this is an animated loop with base reflectivity on the left and base storm relative motion on the right, with the 0.3 kilometer shear vectors overlaid. Those are the white bars. From 150Z to 4Z, I'll just let this play through a few times. You can kind of see what's going on there. We have the strong outbound winds develop east of the RDA site fairly early on in this loop here. You can see we have numerous outflow surges that occur between 150Z and 4Z. And we had a few areas of rotation present, but there was no well-defined or no intense couplets, and we received no tornado reports during this time period. This is a still image from 230Z. Again, base reflectivity on the left, storm relative motion on the right with the 0.3 kilometer shear vectors plotted. So I'm going to go through the three ingredient method here step by step. So for the first ingredient, we're looking for a balanced or slightly sheared dominant QLCS. So the first thing to do is to identify your updraft, downdraft convergence zone using the lowest tilt storm relative motion, which I have outlined there by that dashed white line. And next up, you want to identify specific regions of the QLCS in which the cold pull and wind shear are balanced or slightly shear dominant. So I went through and annotated the slide there. You can see where we're either cool pull dominant, balanced, or slightly shear dominant. In this case, we didn't have any portions that were slightly shear dominant. But you can see that we do have a region that is balanced, and it's encapsulated by that white rectangle. So that's the portion of the QLCS that we are most concerned with for possible mesovortex generation in the near future. To do this operationally, you can use the sample tool and put your cursor, if you're in AWIPS, you can put your cursor over the updraft, downdraft convergence zone in storm relative motion, and then toggle to the base reflectivity and see how closely this coincides with the leading edge of the QLCS. Or if you have a 2-panel, 4-panel plot up, again, the cursor tool will show you, will show up on both the reflectivity and the storm relative motion. You can use that to kind of approximate where you're balanced. Moving on to ingredient 2 now, 0.3 kilometer line normal wind shear greater than or equal to 30 knots. We want to determine the line normal wind shear near the balanced or slightly wind shear dominant region of the QLCS. So again, there's our balanced region, the QLCS at this point in time. And there's our shear vectors, both close to the line at this point in time and then downstream. It's important to look downstream. So there's our shear vector, about 40 knots from about 180 degrees. And our storm motion this time, the line was moving northeast at about 230 degrees. There's our QLCS motion. So applying some simple trig here, there's our QLCS motion, there's our wind shear vector. Applying simple trig, to find that angle between the two, you would just take the motion of the QLCS and subtract that from the shear vector orientation. So we have an angle there about 50 degrees. We want to find x, which is that line normal wind shear. So again, simple trig, we're able to find that our line normal wind shear is about 26 knots. Now, this is the cosine function, so it's not that difficult to approximate it just from the QLCS orientation and movement and the 0.3 kilometer shear vectors. And just knowing what we know from the cosine function, that a 45-degree angle would cut the line normal shear by 30%, and a 60-degree angle would cut that line normal shear in half. Or if you have access to a web browser, you can just throw this into Google, and it will show you your line normal wind shear right there. So it's pretty simple and quick to do. Moving on to ingredient 3 now, we're looking for surges or bows in the line due to either a rear inflow jet or a locally enhanced outflow along the convective gust front. Again, that's our balance region. So indications of rear inflow jet would be possibly a rear inflow notch, a bowing feature, an outflow surge. So in this case, we have a fairly well-defined inflow notch right here with an outflow surge showing up right there, and then you can even see a little bit of an appendage on the leading edge of the line across the convective line from the rear inflow notch. So we did satisfy that criteria. So just a quick little checklist here on the bottom right, going through it again. We did have a balanced or slightly shear dominant QLCS. We did not meet the criteria for the greater than or equal to 30 knots of 0.3 kilometer line normal wind shear, and we did satisfy the final criteria of a rear inflow jet or outflow surge in the QLCS. So 2 of the 3 ingredients were met here, not all 3. Moving on to 4Z, or 10 p.m. local time, we can see we have a fragmented QLCS entering into Bexar County. Bexar County is that county right there, denoted in the yellow outline. San Antonio is right in the center of Bexar County and is completely encapsulated by Bexar County. And you can see we're lacking organization at this point in time. It's kind of broken and fragmented, and there's really no tight reflectivity grade on the leading edge. The QLCS had actually weakened since its earlier state at 230Z, the previous slides I had just shown. However, it was entering into a region with a more favorable environment. Took a 4Z wrap sounding from that location right there, denoted by the yellow star. And most notably, we had a marked increase in the low-level wind shear as this line was entering into Bexar County. So again, I'm going to show an anime loop here. Again, same thing, base reflectivity on the left, storm relative motion on the right with the 0.3 kilometer wind shear vectors plotted. And you can see that QLCS line quickly organizes and strengthens as it enters into Bexar County. You can see evidence of a descending rear inflow jet. We have a bowing segment that forms, numerous outflow surges. And one of the important things to note here is that the tornadic region of the QLCS actually begins moving from about 230 degrees to about 210 degrees as this kind of surges outward and you get that bowing segment to form. And what this did was that it actually gave us a more favorable angle there between our QLCS orientation and motion and the shear vectors. And you can see we have numerous velocity couplets that form over this time period and actually produce 6 tornadoes. So just like before, I'm going to go through the 3 ingredient method step by step. This is a still image from 4:30Z or 10:30 p.m. local time. Again, for ingredient 1, balanced or slightly shear dominant QLCS, you're identifying your updraft, downdraft convergence zone. And then you're identifying specific regions of the QLCS where you're balanced or slightly shear dominant. In this particular case, we actually had a fairly large portion of that line that was classified as either balanced or slightly shear dominant. You can see that by the light outline there. So we definitely met ingredient number 1. Again, ingredient number 2, now we're looking for our 0.3 kilometer line normal shear at or near the location or slightly downstream of the location where we're balanced or slightly wind shear dominant. So there's our region there where we're balanced or slightly wind shear dominant. There's our shear vector is close to or slightly downstream of the QLCS at that time. And we've got about 40 knots at about 175 degrees. Again, our QLCS motion at this point in time, after we get this bowing segment to form, this outflow surge, it's now moving from about 210 degrees. Again, applying the same methodology as before, we want to find our line normal wind shear. We apply simple trigonometry, and we find that our line normal wind shear is about 33 knots. So we are satisfying the second ingredient in this case. And moving on to ingredient number 3, looking for surges or bows in the QLCS. Again, there's our balanced or slightly shear dominant region. That's our shear vectors. And again, you can see a very well-defined rear inflow notch. You can see this bowing feature present here in reflectivity. You can see the outflow surge here on the southern edge of that. And in FSI and AWIPS, or if you're not in the Weather Service or you have access to GR analysts, it's actually much easier. You can take a vertical slice to locate perhaps a descending marine flow jet. So I took a vertical slice here across this line. It's basically an RHI. It's down the radial through the Boeing segment here, and this is storm relative motion here. And you can see pretty clear evidence of a descending rear inflow jet. Pretty textbook example right there. So given all this, we were more than meeting, in fact, we were exceeding ingredient number 3. So going through our checklist again, you can see that all 3 ingredients are satisfied, and we end up having a number of tornadoes that occurred shortly thereafter at this point. I'm going to present it a different way here, just highlighting the locations at this point in time, same time 430Z. This is the region where we were meeting the ingredient of 0.3 kilometer line normal shear greater than or equal to 30 knots. This is the region where we had a balanced or slightly shear dominant portion of the QLCS. And then this dark blue here denotes the region where we had a rear inflow jet or outflow causing a surge or bow in the line. So once you identify this location where all 3 ingredients are satisfied, you have essentially identified the specific region in the QLCS most favorable for mesovortex genesis and thus tornadogenesis, which would be this location right here. Like I mentioned, it's very important to look downstream. What are your shear vectors downstream? What happens if your QLCS begins moving in a slightly different direction? So there's all of our shear vectors located downstream from the QLCS at this time. There's our motion of the QLCS. So from this, we can determine our greatest QLCS tornado threat area for the next, say, 0 to 30 to 45 minutes. So that would be our enhanced threat area during that time period. It's not necessarily a tornado warning polygon suggestion, but just an area that you want to keep an eye on is if we're going to have mesovortices and tornadoes in the near future, it is most likely going to occur in this region. So what happened in real life, we had, in this event, we had 4 tornadoes that occurred in the F2, in the F1, and 2 EF0s, all okay with that enhanced threat area. This is a 4-panel plot from the Ridgeview Alamo Heights EF2 tornado. Reflectivity top left, storm relative motion top right, differential reflectivity, and correlation coefficient. And this was our most impactful tornado of the event. Began at about 10:36 p.m. local time, or about 6 minutes following the still imagery I showed in the previous 2 slides going through the 3-ingredient method. It was on the ground for about 8 minutes and tore through a highly populated area of north central San Antonio. Max winds were 120 miles an hour with a path length of 4.6 miles and a width of 600 yards. And we even had a tornado debris signature present for about 3 volume scans. You can see that TDS denoted within the encircled region. Here are some damage photos from that EF2 tornado here. This is a residential street with some pretty substantial tree damage, some power lines down, and lots of roof damage, even some minor structural damage to the walls themselves. And we actually had civilian air patrol go out and do some surveys for us, and this was a aerial imagery taken in that same location. You can see lots of substantial roof and structure damage as well as tree damage. So I'm going to move on now to a later portion in time here. This is as the QLCS was entering into and in the eastern reaches of the Austin metro area. And it was entering into an even more favorable low-level shear environment. Again, we had numerous outflow series apparent, Boeing segment forms, numerous velocity couplets form over the course of the loop. And we had 2 EF2 tornadoes that were produced in Williamson County. Right about there, you can see those tight couplets form. So since I've already showed how to do this twice already, I'm not going to go into it in total detail, but I will go through it one more time. Ingredient number 1, we're looking for that balanced or slightly shear dominant QLCS. So those are updraft, downdraft convergence zone. And we've located that area right there as our balanced or slightly shear dominant region of the QLCS. So check mark there. Next up, our line normal wind shear. There's our shear vectors along the line there. We have about 50 knots at about 185 degrees. Our motion is still at about 210 degrees. So same process as before, doing that trigonometry. Now the angle is even less. And so that actually enhances not only that angle is smaller, but our shear vectors are actually larger in magnitude. So now our line normal shear is up to about 45 knots. So we are exceeding that by quite a bit. So that criteria is satisfied. Then lastly, an RIJ or outflow surge in the QLCS. We have another rear inflow notch right here, a little smaller Boeing feature there in reflectivity, and a bit of an outflow surge there as well. So that criteria is also met. So we are satisfying all 3 ingredients during this time period. Similar as I showed on the previous time period here, just denoting where all three regions, where each ingredient is satisfied. And again, this is the location right here where all three are satisfied. So this is our region that we are most concerned with for mesovortex genesis and tornadogenesis. Again, we're looking downstream, looking at our shear vectors. We got 45 to about 40 knots, still at about 185 degrees, so still very favorable orientation of those vectors. There's our motion. And so again, we can use this to determine our greatest threat area over the next 0 to 30 or 45 minutes. And we actually had, like I mentioned, 2 EF2 tornadoes that were produced in far eastern Williamson County. This is the Thrall EF2 tornado. Williamson County began at 12:25 a.m. local time, on the ground for about 8 minutes. Max winds 120 miles an hour. This one's actually on the ground for 9.4 miles, which is a pretty substantial path length for a QLCS tornado, with a width of about 200 yards. And again, we had the tornado breach signatures present for about 3 volume scans. This tornado actually crossed this highway here, and there's a railroad track that runs parallel to it. And there just happened to be a train coming at the time that the tornado crossed and was able to flip this train over on its side. So with that, I will turn it over to Jared briefly. He will go over some best practices.
Great. Thank you, Brett. Really appreciate it. So obviously we went through a good amount of research, and then we went through the application of that research. Well, how do we kind of bring that all together into a Weather Service operations perspective? As with anything dealing with severe weather or any communication message regarding a forecast, it needs to start with good communication. So if you have a designated meso analyst or an event coordinator, they can brief the radar warning team either at the beginning of the event, prior to the event, or at least potentially every 30 minutes, depending on the QLCS evolution. So as an example, one can, as an event coordinator or even the radar warning operator themselves, they can overlay the RAB 0 to 3 kilometer shear vectors on a regional perspective radar or even the site radar to make sure that they have the greater situational awareness. So whether you're the meso analyst or the event coordinator, a very simple situational awareness sentence that can be thrown out there, depending on the environment, would be like 0 to 3 kilometer shear vector is about 35 knots from 220 degrees. Therefore, any north, northeast, or maybe even northeast surge that you see could potentially favor mesovortices. And that type of information can kind of sit there in the back of the warning operator's mind to know if they ever see or potentially see that surge, and then they see it becoming balanced or slightly shear dominant, and then therefore they know what the 3 kilometer shear vector favorability is, then you have all 3 of those ingredients ready to go. You have the concept in your mind, and therefore you set up that enhanced tornadogenesis threat location to enhance your awareness on potentially where you're going to actually put out a tornado warning itself. So, and maybe during an event itself, where you're a little bit further down the line, 30, 45 minutes later, it looks like it's starting to bow out now. I see increased inbounds in the rear inflow. Looks like it's becoming better balanced. So if you have that balance, you have that surge, and then you have the supportive shear, all of those concepts from the research to the application can really be applied into warning operations. So as we went through those key ingredients listed again, 1, 2, and 3, that those stay conceptually. Even you can have a checklist maybe right in front of you if you want, or just kind of review this on occasion to make sure that you're fully situationally aware during QLCS situations. So here are just a couple examples real quick. You can overlay the 0 to 3 kilometer shear vectors from a regional or a site perspective. You can toggle it on and off really fast to make sure you don't clutter the warning operator screen if you're the actual warning issuer. Or the meso analyst can have it on their computer or screen, or they can project it up on the big situational display where everyone can see in the office, and they can brief off that to make sure everyone is well communicated on the evolving meso environment. One other recommendation as well, I know this is certainly stated, the Warning Decision Training Division as well with the RAC and DLOC courses up there, where you have that 4-panel combination of the lowest radar tilts. Sometimes when you have that rear inflow jet that's descending, it helps create the tighter couplets higher aloft, say at 1.8 to maybe 1.5, just prior to the 0.5 or the 0.9. So if you're just solely looking at velocity and reflectivity on the 0.5, it may not be as quick as an indicator versus looking at a little bit higher up where you initially get that surge and that you get that tighter couplet higher up first before it descends down at the lower levels. And lastly, say, what if you are not in the Weather Service office? What if you just want to look at the 0.3 kilometer shear vectors online? Well, you can actually look at that on the SBC Mesoanalysis page. 2 days ago, there was a pretty gnarly squall line that went through Georgia, South Carolina. I know they're dealing with some more stuff today as well. But this is a screen capture from a couple days ago. And you can see that you had the nearly 40 to 35 knots almost due north, a little, maybe about, looks like 190, maybe 200 degrees. And then whenever you had surges to those angles that were supportive, you had a lot of tornadogenesis along that line. This can be found under the multi-parameter fields.
All right, you're just going to go over a little bit of future work. Jared and I have compiled a database of all QLCS tornado events dating back to October 2005. For the domain of most of Texas, you can see the region highlighted here. A lot of work has been done on QLCSs across the Central Plains, Midwest, the Ohio, and Tennessee valleys, but to our knowledge, there really hasn't been a whole lot of detailed work done on our region down here. So that's what we're setting out to do. The goal is to examine some radar environmental characteristics and apply the 3-ingredient method to see what percentage of tornadoes or mesovortices it correctly predicts for our QLCS events down here in Texas. And lastly, some acknowledgments. First and foremost, Schaumann and Pryzbylinski. We drew a lot of stuff from their paper in 2012. And just a brief word about Ron. Ron, as many of you know, was one of the founding fathers of QLCS research. Ron was incredibly intelligent and passionate about his work. But above all about Ron was that he was incredibly caring, compassionate, and overall a decent human being. Sadly, Ron passed away a couple of years ago, but I think I speak for all of us when I say that Ron is dearly missed. But the contributions to our field, his warm personality, and his kind heart will always be remembered by us here in the meteorology field. And then Stanford et al. It was a Howling Scholar project. John Gagan, formerly of the Weather Service office in Springfield, now at Milwaukee, and Jason Schaumann again. And lastly, I want to thank the Weather and Forecasting Committee for their review and support of this presentation and for allowing us to come on here and speak with you guys about this. And lastly, thanks go to the National Weather Association. If you have any questions or comments or just want to contact us about anything, you can find both Jared and mine emails listed there, as well as our Twitter handles. And with that, we will take any questions.
All right. Thank you so much, Jared and Brett. This is fascinating information. I'd say it might have been very helpful for us to have this last week for our little QLCS event that we had on Monday, but that's neither here nor there. I do have a couple of questions on GoToWebinar. I don't know if Dan has any on Twitter, but I'll go ahead and start with some of the GoToWebinar questions. There's one question from a guy. He says he lives in the Roanoke area of Virginia. He's been researching lee-side convergence east of the Blue Ridge Mountains, and he wants to know if you think that lee-side convergence along with vorticity stretching maybe produces more tornadoes than to the west slopes of the mountains. And what are your thoughts on that, if you have any?
That's a very excellent question. I would say anytime that you have a likelihood of enhanced convergence, especially if you have a stronger lee-side cyclone genesis on the mesoscale or subsynoptic scale, that in itself could potentially act to enhance the localized 0 to 3 kilometer shear vectors. So it is possible that potentially on the lee side, like the Rockies, or the lee side of some mesoscale or mesoscale environment, those shear vectors could potentially be a little bit more enhanced. But I think a lot more research potentially might have to be done in that area to have a full conclusion.
Okay. Dan, do you see anything on Twitter? We can sort of go back and forth with this.
I do not right now, but as a reminder, if you do have a question, it's hashtag NWAWebWed, just as Tricia said at the beginning, but just as a reminder, hashtag NWAWebWed. And I will go ahead, Tricia, and give it back to you.
Okay. Brett, when you were going through your case studies that you have, you referred to the term balance, and so I have a question here. Is that referring to the signatures of velocity?
Right. So let's see if I can go back. Bear with me here as I try to go back. So when we're talking about whether it's balanced or shear dominant or cool pull dominant, the main thing we're looking at is, this kind of goes back to, Jared kind of set this all up on one of the first slides when he was showing the visualizations there of what happens when you have, it's either cool pull dominant, you have a much more shallow updraft. When it's balanced, you have a much more upright updraft, which is going to help you with your tilting and stretching of horizontal vorticity into the vertical. So to do this simply on radar, almost there. Just realizing how much animations I had as I go through this. Sorry. So the key thing that you want to look for is you want to see, here's your storm relative motion. So there's that location there separating your inbounds from your outbounds. That's your updraft, downdraft convergence zone. And so over here you can see where your reflectivity kind of lines up against that. So in this region right here, you can see the leading edge of that convective line matches up really well with the updraft, downdraft convergence zone. So at that point, that tells you that you're pretty well balanced here between your cold pull and your wind shear. This example doesn't show it. Here it's slightly shear dominant. You can kind of see we're having some echoes from the leading edge of the line kind of come across from where the updraft, downdraft convergence zone is. So your wind shear is actually stronger than your cool pull, so it's kind of punching that outward almost as if like you had a weak echo region there. In the previous example, if I can get back to it in time, you can see we had regions of the line where it was cool pull dominant, and that is noted by, let me get back to it. So in this case right here, up here on the northern edge of this and the southern edge, especially down here on the southern edge, you can see that here's our main convective line of that QLCS, and it's pretty far removed from our updraft, downdraft convergence zone. So at this point, your outflow is actually overpowering your wind shear. And so that's how you can determine where you're balanced or where you're cold pull dominant or where you're shear dominant. I hope that answered the question well enough.
Okay, another question here. Does the inclination for tornadogenesis occur along updraft, downdraft convergence zones, or is the zone more of a periphery where one should begin looking for rotation?
When that zone is balanced, and especially when you have the shear vectors that align with it the best, you're obviously when you're getting mesovortex generation, it is becoming, it's either balanced or slightly shear dominant, because you're obviously the tornado mesovortex itself is a lot of shear very locally. So that in and of itself, you look for it to be either right on the updraft, downdraft convergence zone, or it can be slightly ahead, because just as Brett mentioned, whenever you have that slightly shear dominant regime, it's going to be slightly ahead of that up downdraft convergence zone line, where you kind of get that little potential hook or a potential append.
Okay, Dan, you have anything yet?
No, I do not.
Okay. There is a comment here from John Gagan. He says that he and Jason Schaumann are both on the call, and great job by both of you. Wonderful case. There's another question here. How would you handle, or how does your office handle warnings, severe and tornado, with these types of situations?
Well, these are fast evolving situations. So what we always try to make sure of, once we see that balance is occurring, especially in balance or shear dominant regimes, certainly if we feel that the severe straight line threat is there, we'll clearly have a severe thunderstorm threat warning out for it. And then given some of the new IBW impact-based warning tags, we will very likely have a tornado possible tag within that severe. Now, once you have that larger severe polygon out, we will obviously then look for where those smaller couplets develop along those balanced to slightly shear dominant regions whenever you have those three ingredients line up. And then will issue, obviously, the tornado warning itself based off that, likely be initially radar indicated. But certainly in this case, where we had several TDSs, we'd use tornado observed potentially from the TDS observation. So clearly cover it first with the severe, with the tor tag possible, and then obviously whenever you get those small couplets, really tighter couplets, that's obviously when you do the tornado warnings themselves. In this particular case, it would probably start at 30-minute tor warnings, given the amount of time that generally these mesovortices stay intact. Generally, QLCS tornadoes don't last too long, opposed to supercell tornadic mesocyclones. But that would be generally the approach that we would take.
Okay, I have another question that was relayed here. So the question was, so if I'm reading these correctly, I'm assuming that the horizontal rear inflow jet mixing with the vertical updraft, downdraft is what creates rotation?
Did you say can you repeat that one more time?
Is it that the horizontal rear inflow jet mixing with the vertical updraft, downdraft, is that what creates the rotation?
That certainly helps enhance it. Depending on how a rear inflow jet comes into the backside can really help balance a local segment. So once you get that local balance, kind of going all the way back to the very beginning, if you have that balanced cold pool and shear environment or a slightly shear dominant regime, you're able to really enhance that updraft, downdraft convergence zone. So if you're enhancing that low-level 0 to 3 kilometer layer of interaction where you have those initial horizontal rotors and then you're able to tilt those into the vertical, the rear inflow jet could potentially aid in that full process.
Okay, and the last question I have, it's kind of a long one. It's from a listener that's over in Europe, actually. He's asking, have you seen cases of QLCS systems in very low cape, strong shear environments where the evolving QLCS would be very shallow, that is, just a few kilometers high with weak lightning? And if so, would the 0 to 3 kilometer shear vector still be applicable, or would using a smaller or lower layer be better in those cases? Apparently, they often have situations in Northwest Europe during the winter months in strongly forced environments with shallow convection but very high low-level shear. So basically, again, to summarize the question is, if it's very shallow, would there be any situation where you'd use a lower shear vector rather than 0 to 3 kilometer?
Yeah, I'll handle this one. So I've done quite a bit of QLCS work. My master's thesis was on QLCS, so I've looked at a lot of cases from multiple regions across the United States. And going back to what he said, in many cases, these QLCS tornadic events occur within highly sheared environments, but very below instability. Some cases even like less than 500 joules per kilogram in most unstable cape. So that does happen a lot, those high shear, low cape environments for QLCS tornadic events. In which case, if you have very shallow, very shallow depth QLCS at that point, something like the 0 to 1 kilometer, the 0 to 2 kilometer may be more applicable. In some of the work that I've done, I've noted that 0 to 1 kilometer shear vector is also a fairly good indicator of, if you're above a certain amount, pretty similar to the 0 to 3 kilometer shear. If you're above that 30 knots, 0 to 1 kilometer wind shear, that's pretty favorable for mesovortex generation. So, yeah, certainly if you're in a more shallow, QLCS, looking at some of those 0 to 1 or 0 to 2 layers may be more helpful than, say, the 0 to 3 layer.
All righty. Well, Dan, do you have anything else?
Yeah. Over Twitter, Greg Higgins asks, did you warn during the event using this method in this case study?
Not fully. I was relatively and somewhat aware of this particular methodology from my time back in Jackson, Mississippi, where I used to be in the Weather Service office there. And obviously we got a lot of QLCSs there, and obviously through the mid-Mississippi Valley as well. I was partially aware of it, but given the time of shift change / coming on board right at 10 o'clock being the event coordinator, and then 30 minutes later going from a very outflow dominant, relatively weak QLCS to mesovortex generation all over the place over the next 2.5 hours. It quickly evolved. So we didn't actively and fully apply this 3-ingredient method during the actual event, but it was somewhat cognizant in the back of our minds, certainly as we started seeing the mesovortex generation just spin out of control once it got to Bexar County.
Alrighty, well, we have gone a little bit over an hour, so we will go ahead and end it. Thank you so much, Jared and Brett. Like I said, this is fascinating information. It's a great presentation. This presentation has been recorded, so we will have it available on the NWA member page, so we'll have a link to watch the recorded presentation on there. So if you go to your member portal, it'll be uploaded there at some point. I've got to get it converted first, but in the meantime, we're going to be looking forward to our NWA WED presentation next month, which right now should be on the NWA awards process and will be held on Wednesday, May 3rd. More information for that will be forthcoming, but again, thank you, Jared and Brett, and thank you also, Dan, for helping to facilitate. And I know Tim Bryce he's on the webinar team. He's been sort of helping to monitor as well in the background. Thank you all very much, and have a good rest of your morning or afternoon.